So the next conversion factor that we are learning is the molar volume of a gas. So if we have a gas, gases take up a certain volume. And it was actually Avogadro who is credited with this discovery, that it doesn't matter if it's the gases carbon dioxide or argon or neon, any gas, no matter its identity, will have the same volume if you have the same quantity, the same number of gas molecules. And that would be at the same temperature and pressure. So what we have done is decided, okay, this is going to be the standard temperature and pressure for all gases. So anytime you see this STP, that's what that stands for, standard temperature and pressure. It's the actual numbers or 1 atm of pressure, which is about the atmospheric pressure that we feel around us right now, and 0 degrees Celsius or 273 Kelvin. And that, of course, is quite a bit colder than the outside temperatures are. The story that I have been told is the reason why standard temperature is 273 for gases is because a lot of the scientific research that has been done on gases was done in Scandinavia, where it just is always much colder. So a lot of their work was done at much colder temperatures. So it just made more sense to do 0 degrees Celsius. So what we've learned is that if we make sure that the gas is 0 degrees Celsius and 1 atm, that no matter what gas it is, 1 mole of it will always have a volume of 22.414 liters. And that is another number that we are going to store in our calculators. I would store that under alpha L for liters. So remember, you would plug in 22.414, then press enter, and then press the store button, alpha L, and then enter, and then that'll be in there for until your computer batteries die or whatnot. So now this is another conversion factor. We are going to be using this conversion factor for a whole slew of problems here, and then we're going to sort of notice, hey, if this is also equal to 1 mole, then those problems that we just did, we can also incorporate molar volume of a gas in there. So the first question that we have is, what volume does 3.55 moles of helium gas occupy at STP? And all these problems should state at STP, because if we are at a different pressure or we are at a different temperature, the volume is going to change. It's not going to, this relationship is not true. So you can only use this number if you see STP in the problem. And that's it. Students will use this incorrectly many times, and that's what my advice to you would be. We can only use this if the conditions are standard temperature and pressure, which are 1 atm and 0 degrees Celsius. So of course I circle the do, underline the clue, take the clue, and put it out front. 3.55 moles of helium. Right? And I use this conversion factor right here, matching up the units. So mole out front means mole down bottom. And then, of course, 22.414 liters up top. In my calculator, I plug this in. I get 79.5697. Then I take a look at my significant figures. This number does have significant figures. In a lot of textbooks, they only use 3 significant figures for it. The College Board for AP uses all 5. Therefore, I'm going to use all 5. And but still, we're going to cut this one off at 3 significant figures. So my answer is going to be 79.6. And of course, my mole units will have canceled. So 79.6 liters of a gas at STP, at standard temperature and pressure. Okay, we have another problem like this. You can try this. If you feel like you got this, pause it and try. I'm going to go through this whole one together. How many moles of carbon dioxide are in 50 liters of carbon dioxide at STP? So 50.0 liters of CO2 And it's the same conversion factor every time. This one does not differ based upon the identity of the gas like molar mass does. So 1 mole will go up top, right? Because whatever I'm converting to needs to go on the top. And 22.414 liters of carbon dioxide goes on the bottom. So in my calculator, 50 divided by 22.414, I get 2.2307. This number has 3 significant figures. This number has 5. So I want my answer to have 3. Cut it off there. The next number is a 0, so I don't need to round up at all. 2.23. And the units will cancel. So that will be, right, moles of CO2. Okay, now we could talk about putting all of these together, because what's tying them together is that they're all equal to 1 mole. I know that the volume of a gas at STP, 22.414 liters, is equal to 1 mole. I know the Avogadro's number, 6.022 times 10 to the 23rd particles, is equal to 1 mole, and I know that the molar mass, and that will be dependent on each substance, is dependent on 1 mole. So if these 3 things are all equal to 1 mole, that means that they can all be equal to each other. We can be doing these problems in 2 parentheses, or we can do them just in 1. So we call these mixed conversions because they just have everything in them. So the first one says, convert 4.66 grams of sulfur dioxide to liters of sulfur dioxide. This should say at STP. That's an error on my part here. Circle the do. What do I want? Liters of sulfur dioxide. Underline the clue. So I know if I think of, for sulfur dioxide, this would be for every compound. 1 mole is equal to 6.022 times 10 to the 23rd particles, and is equal to the molar mass in grams. And that would also be equal to 22.414 liters of a gas at STP. So if the substance isn't a gas at STP, we could never use 22.414. But this sulfur dioxide is a gas at STP. So I'm going to take my clue, the 4.66 grams of SO2, that's sulfur dioxide, and put it out front. Right now, all these 4 things are equal to each other. So that means I can put any of them anywhere in my parentheses. These are like, let's see, 36 inches, 3 feet, 1 yard. All those things are actually the exact same thing. So they're all equal to each other. Just like these 4 things are all equal to the same thing. They're all equal to each other. So I can put them in parentheses because they are conversion factors. The molar mass of SO2, so 1 sulfur, 2 oxygen, is 64.07 grams. And I want to go 2 liters, so I'm going to put liters on the top. And that is, of course, that number, 22.414 liters. And in my calculator, multiply by the top, divide by the bottom, 1.6302. And then I go check for significant figures. This number has 3. This number has 4 because it came from the periodic table. And 22.414 has 5. So I'm just going to round this to 3. So 1.63. And then notice that my grams units cancel. So that would be liters of SO2. And then I like to write at the end at STP because that will not be true at any other temperature or pressure. Okay, here's another problem. Convert 9.00 times 10 to the positive 24 formula units of magnesium chloride to grams of magnesium chloride. Right, so remember we're still using these kind of 4 conversion factors here. I take the number that I want to convert and I put it out front. Formula units of magnesium chloride. Right, match up. Whatever unit is out front has to be the unit down bottom. And you may say, well, formula units isn't up there, but formula units is a particle, right? Atoms, molecules, or formula units. That is what goes with Avogadro's number. So 6.022 times 10 to the 23rd formula units of MgCl2. And then since I want to go to grams and what I'm converting to, I'm going to put on the top, I find the molar mass of magnesium chloride. And on the top, we are converting to grams. So the molar mass of magnesium chloride is 95.21 grams. And then, of course, I multiply by the top, divide by the bottom, and I get 1422. And then take a look. 3 significant figures, 4 significant figures, 4 significant figures. So I'm going to round my answer to just 3 significant figures. So this doesn't equal 142, right? How can 1,422 round to 142? That doesn't make any sense. We have to put an extra 0 there to hold that place value. But if I don't put a decimal point, that means that that 0 stays not significant. My units cancel out, so I'm left with grams of magnesium chloride. Okay, so the most important thing that we really got out of this section right here is knowing these 4 conversion factors. And now I can interconvert between the 4 of these in really just one parenthesis because they're all actually equal to each other.